opposite of that. It's B minus 3, right? So it would be if we get it like a thing, like a position, so the first position would be P minus times P minus 1, right? That would be the first position. And that would be M, right? I had to wait on to come up with this.
Did you?
I don't know. Can I use my knife? Your haircut looks nice.
What was it? Oh, I hadn't even got that far yet. I'm still trying to figure out which one it is. It took me 45 minutes to do a problem that I did more than I was supposed to do.
Last week, I had my homework filled out ready to go. And I had to sit down, and I taxed it up to Sheila, and she said, "Where's your homework?" I said, "Oh, I forgot this community." I like some picture of what it's into. Like, she should be like 11.
Okay.
She might as well.
That's okay. She doesn't like it. We, that's what they call us, and we call somebody, not really call us. So I was like, so,
That's great.
yeah, we're already at skeleton crews, and now it's getting worse. So I have nobody to work right now, but I set up and the problem, Bruce down the hall.
The only thing she ever has problems with is sometimes
The overhead,
if she gets it like started.
we go and work on it now, but.
Yeah.
It was 7:26. That's usually.
So they're going to go on.
I've got number 7 and 26. Did you just solve 26, 4.1? Like I just solved it.
Yeah,
It just felt weird.
I was glad that,
It's zebra pick it. So good.
Oh my goodness. God, number 7.
Oh, yeah.
Yeah. 4.1.
What now? What number? I don't know. I don't know. Sure it wasn't there? Oh, never mind. Just
Oh, but he's going to hate me.
yeah, it's not bad. I just made a paper.
I got a new job last week, and what happened is out of 4 shifts, so all day yesterday, I was there. I didn't get on.
That one we charge. Yeah. Wait. No,
She was like that, and then here's what
Okay.
that's all she got.
CD.
Questions, but I just get supplies and stuff. Nice.
We're and like this weekend.
I'm telling you what.
What? Point about it.
Usually nothing comes up. I guess the question is, videos are not recorded or not posted on that server. So for some classes, like 1 or 2 classes,
Really?
who should I contact for that?
We contact admins to find out what's going on. That's usual. Sometimes it takes about 24 hours when you get the stuff.
Well, it's more than, it's like 1 or 2 classes. It was like 3 weeks ago. And last week, the second class was
I wonder if like one day on one computer, then another day.
different sofa. Okay, I can check the other.
You get the professor? You get the professor?
Tyler.
Yeah.
Can you just mark for a little bit?
Yeah.
You're walking, you can leave it.
Oh, really?
Okay, I can see it.
Yeah, that's fine.
You see it?
Yes. And
Yeah, if you need anything, no, I'll come.
Megan. Here. Elsa.
Here.
Morgan. Here. Allison. Katie. Katie. Jessie.
Here.
Leah. Here. Catherine.
Here.
Curtis.
Here.
All right. Any question about homework? Number, which one? 28? Oh, it's, you're talking about difference of, do we have a 28?
It wasn't on the list, but it was in the last one.
Oh, okay, I didn't put it on the type. Do you all have the book? 28? Okay. So when you do number 28, let me write down a question. You are going to follow the one we did in class exactly the same way. So we want to prove the implementing compliance. Do you remember what number I created in class? In order to get a contradiction, what was the number that I recreated in class? You can look at your notes. I don't expect you to memorize immediately, but so when we did that, the question was to prove there are infinitely many high numbers. What we did is indirect proof. By way of contradiction, we assume there are finitely many prime numbers.
Does anyone remember so we say there are finite prime numbers, which we listed them as P1, P2, all the way P2 to Pn. And after that, we constructed a number that we proved it is prime, and also it's not one of those prime numbers, which is a contradiction because we are claiming all the prime numbers are here. So that's all the prime numbers. And then we found out another number which is also prime, but not in here. Does anybody remember the number we created? Can look at your notes. What was that? Dana, do you have it in your notes? Huh? Yeah, but what is n? Did you all take notes? It's also in the textbook. That was an example from a textbook. It's on page 183 in the old version. I guess the third version, if you have other editions, under the section 2 classical theorems. Did everybody take notes? So let me show you again. I do have that from last time, so we can go over this example one more time. We want to prove the set of prime numbers is infinite, which means we want to prove there are, in other words, we want to prove there are infinite many prime numbers. So because we cannot prove it directly. How do you prove it directly? You will have to list the infinite many prime numbers, which we can't list anything that has infinite many numbers. So what we did is we assumed that there are finitely many prime numbers. If there are finitely many, finite means there is an end. Infinite means there's no ending. So if there is a last number, last prime number, we can list all of them. So this is what we did. P1 is the first prime number, which is 2. P2 is second prime number, and third prime number, ... And Pn will be our last prime number because we assume there are finitely many. Okay, after that, we try to create a number which is right here. That's what we created. We take all the prime numbers we have, and multiply them, which will give you a huge number, incredibly huge. Because when you do multiplication, the number gets very big. And after we multiply them, we also add 1 to that number. If you don't add 1 to it, what kind of number is this? When I say what kind, I mean prime or composite. It has to be composite, right? Because if you can break down a number as a product of prime numbers, it has to be composite. But our goal is to create a number such that number is not a composite, which is prime. So that's why we add 1 to it. That will make it a prime number. How do you prove this is a prime number? So if you can look at the process we did. I'll go over that in a second. So the homework question is exactly the same, but the number they created is not taking all the prime numbers. P1, P2, what they ask you to do is take P factorial. That P, so that's the number they created is, compare what we had. One type of P factorial. Have you all learned factorial, the simple factorial? If you have not, factorial means, we will talk about this in this class. You may have learned it in statistics. So 1 times 2 times 3 ... all the way to the last number T. So for example, 5 factorial means 1 times 2 times 3 times 4 times 5. So P factorial means 1 times 2 times 3 all the way to P. So this is the number they created and plus 1. So the number, P factorial plus 1. So we add a plus 1 to that. So what you will do is you can prove that this number, let me rewrite it. You don't have to use factorial. You can just use 1 times 2 times 3 ... times P plus 1. So this is the number you created. You want to prove this is a prime number. Okay. The proof, how do you prove this number is prime? the proof is exactly the same as what I did in class last Monday. So that the number I created is P1, P2, P3 all the way times to Pn. All of these numbers are prime numbers. What you have, they may not be prime. For example, 1 is not prime, and next number 4 is not prime. You're including composite numbers, but mine only includes prime numbers over here. But the way you prove it is going to be very similar. So how do I prove this is a prime number? This is what I did. I want to show now this divides the number I extracted. So this is what I did. I did an indirect proof again. Again, the definition, what is a prime number? Only number that divides that number is 1 itself, right? So in order to show this number is prime, I have to show no other numbers divides this except 1 itself. But instead, I did indirect proof again. So I assume that a prime number does divide that. So I assume that P1 divides N. If P1 divides N, P1 divides the difference of N and the product. And that comes from one of the homework assignments. You can look at, I can show you that homework assignment again. So I did show you in class. Chapter. So number 16, under section 3.3, we proved if A divides B, if A divides C, then A divides the difference of those two numbers. You see that? Okay, we already proved it. So you can use it here. So that's what I used. P1 divides N. Why? That's our assumption. My goal is to prove P1 does not divide N, but I'm going to assume, to the contrary, P1 divides N. And also, P1 divides this product. Right? Okay, I remember I asked this in class last Monday. Somebody answered. I forgot. Was that James or somebody else, Curtis maybe? Somebody said because P1 is one of it, right? If P1 is one of them, of course P1 divides that, what you say goes in there. So P1 goes into N, P1 goes into the product. P1 should go into the difference, to divide the difference, right? Okay, and what is the difference? Go back to that. N equals P1, that's what the number we created. N equals P1 times P2 times P3 times Pn plus 1. So if I move this product to the left, I get, by algebra, I get N minus P1, P2, Pn equals 1. So this difference right here is exactly equal to 1. We're going to get a contradiction. It says P1 divides 1. What does P1 divide 1 mean? Because P1 is a prime number. The first prime number is 2. So it's like saying 2 divides 1, and that is impossible. So right from right here, we got P1 divides 1. That is impossible. P1 does not divide 1. We got a contradiction. The contradiction tells us P1 does not divide N. Similarly, in a similar way, you can show P2 does not divide N. All you have to do is to replace P1 with the P2. P2, you assume P2 divides N, you end up with P2 divides the difference of N and the product, which is also equal to 1. So you got a P2 divides 1, which is also a contradiction. Similarly, if you change it to P3, you get a P3 divides 1 contradiction. All the way to the last one, Pn divides 1. Every single time you replace P1, you get a contradiction. That tells us P1 does not divide N, P2 does not divide N, P3 does not divide N, P4, P5, all the way to Pn does not divide N. If none of the prime numbers divide N, what kind of number is that? Prime number. Okay, I did also give you an example in class, like to explain why is 29 a prime number. I mean, I think everybody knows, yes, 29 is prime, but if you want to explain to someone who don't understand what a prime number is, what you did is to take all the prime numbers, say, okay, 2 doesn't divide 29, so which means you cannot factor 29 as 2 times something. 3 doesn't divide 29, which means you cannot write down 29 as 3 times the integer. Similarly, 5 doesn't divide 29, 7 doesn't divide 29, 11 doesn't, 13 doesn't, 17 doesn't. So none of the prime numbers we have divide 29, which means there's no way to break down 29, right? The only way you can break down is 1 times 29. You cannot break down as 2 times something or 3 times something or 5 times something or anything. So that tells you 29 is prime. So similarly, I did exactly the same way with the variables. I don't have specific numbers, but I have variables. How do I prove n is prime? I take the prime number, like 2 doesn't divide that number, 3 doesn't divide that number, 5 doesn't divide that number. So all the prime numbers we have don't divide that number, which makes it a prime. Exactly the same reason why 29 is not prime. Because none of the, so this is like P1, this is P2. With the number, you can check 2 doesn't go in there, 3 doesn't go in there, 5 doesn't go in there. Without the specific number, I don't know what n is, n is the number. Then I use the indirect proof to prove that it's impossible, there's a contradiction. If P1 divides that would, if P1 divides that, that means P1 divides 1, which is impossible. So that tells you P1 cannot divide n. So similarly, we proved that every single prime number we have does not divide that, makes it a prime number, right? Okay. So when you do your homework, that question 28, they ask you to, they want you to use this product instead of the product of all the prime numbers. But the way you're going to do it is going to be the same. You're still going to take all the prime numbers, and so you can use the same thing we have, all the prime numbers we have. You prove exactly the same thing. P1 doesn't divide this. P2 doesn't divide that. And how do you prove it? You do the same way. Use indirect proof. So if you follow the proof I did last time, it's going to be exactly the same. But when you write it, make sure you don't use P1, P2, Pn. You are using this one, this number you construct it. Okay. But everything else is exactly the same. Okay, so when you write it, all you have to replace is, here it's 1 times 2 times 3 times all the way to n. And you're going to show the same thing. All the none of the prime numbers divide that number you have, this number. So you need to show P1 doesn't divide m, P2 doesn't divide m, and ... Pn does not divide m. And how do you do that? Exactly the same way. Suppose P1 divides m, and you're going to get exactly the same contradiction. And you can say P1 doesn't divide your m, and the same. Okay. All right. Is that clear? Thanks. Yes. Okay. So when you plug it in, you're going to see, well, instead of having n, you have m, right? But if you assume P1 goes into m, you're going to have m here. And P1 also is one of the numbers. So let me rewrite over here. So maybe, this part is going to be, the one you are going to get will be m minus 1 times 2 times 3 ... times p instead of P1, P2, right? So P1 goes into m. That's the assumption. Can you explain why P1 goes into the product? Can you explain why? The same reason. Because P1 is has to be one of the numbers you have. Okay. I guess you do have to say that P is going to be, what's this number P that you use? This P is going to be a number greater than or equal to that one. Okay, make sure when you create a number, make sure your P is greater than or equal to Pn. Why do I have to have that? If this P is bigger than P1 all the way to Pn, that will guarantee P1 is one of the numbers in here. Right? For example, P1 is 2, of course, it's one of them. But what if Pn? But because P is larger than Pn, so Pn is going to be one of them. Okay, so if Pn is one of them, then Pn divides this. and Pn divides m, then Pn should divide difference. And again, that is also equal to 1, so that's still get a contradiction. Okay, so that homework 29 is asking to imitate writing the proof that we did in class. You just have to make some slight modifications. Okay? All right, if you still have trouble doing that, you can try to follow the example I have. If you say you don't have the notes, you could go. I do have, like I said, all the classes are being recorded, and so if you need a video for the class that I forgot to take notes or I missed the class, and you can always send me an email. I'll send you a link to the videos, and you can watch the video again. So for that question there. If you took notes, you can pretty much follow the notes to do that 29. Okay, other questions? No? No question about the mathematical induction?
What?
Okay. Oh, did I switch it back or not? Okay. Yes, it is on paper. Now, today we're going to continue mathematical induction. A practice exam will be posted on Blackboard this week. It's actually already there. I can make it available. I forgot to bring the copy here, but if you want to come to my office, I can give you a copy today, or you can wait until Wednesday. It's up to you. All right, so a copy is posted under on Blackboard under week 8, which I just made available. So the first exam, I think you saw your grades on posted on Blackboard, and I would say most of you did it very well. We actually have 3 perfect scores, which never happened before, and in the past. We never had a class with 3 perfect scores. So I think it was, I know Morgan, is that Katie, and I forgot another student. So anyway, but the second exam is going to be much harder than the first one because we're going to have, you can see there are a lot of proof problems. The first one, proof by cases. Second one, indirect proof, which we just covered. And third one is also indirect proof. Fourth one, indirect proof. Number 5, mathematical induction. And number 6, mathematical induction. Number 7, mathematical induction. So there are a lot of proof problems. Like I said, it's going to be much harder than the first exam. 8, 9, 10 should be a little easier about set notation. 11. Number 12 is also a proof problem. Which is also very hard one. In chapter 5, set theory, we most questions are going to be like about the definitions, but we are going to do one type of proof problems. So number 12.
You can't see the computer screen.
You can't?
No.
Okay, well, unfortunately, we don't have an operator here today. So I guess you will just have to, so you just have to look at on the Blackboard. It is posted on Blackboard right now. I can show you maybe next week. Okay, so where my point is, on the second exam we will have a lot of proof questions. I think when I'm counting it, there will be 8 proof problems. Okay, and okay, so let's continue mathematical induction. I did one example last time to prove 1 plus 2 plus 3 plus ... plus n equals. So let's go over this example one more time. The steps of mathematical induction. And by the way, homework 6, we did indirect proofs. I think most of you did okay. I do want to make sure when you do indirect approach, the first step, follow the certain steps. Step 1, you always assume BWC, you don't have to write that, but you always assume or suppose the negation is true. You do have to write that down. Negation is true. Okay, and I think almost everybody did that. And then the step 2 is to get a contradiction. Try to get a contradiction. And so all you have to do, I noticed some students try to go between direct proof and indirect proof. So if you want to use indirect proof, all you have to give us is a contradiction. There's one question, the last one, to prove homework question is to prove that if the sum of two numbers is greater than 35, greater than or equal to, let me take a look. Let me go over that question before today's class. So chapter 3. It says the sum of two numbers is less than. Two numbers is less than 50. At least one of them. At least one of them is less than 25. So the first step, you do negation. Say the negation is true. So suppose, by way of contradiction, suppose both of them are, we can call both numbers. Both numbers are greater than or equal to 25. So we're going to call those numbers A and B. So which tells us A is greater than 25 and B is also greater than 25. Greater than or equal to 25. Don't forget the equal sign. The opposite of less than would be greater than and or equal to. Now, after we add them, we're going to get A plus B is greater than or equal to 25 plus 25. That gives us 50. This comes from algebra. When you add both sides of inequality, you still can keep that inequality. So we end up with A plus B is greater than or equal to 50. And when you get here, all you have to say is, contrary to the hypothesis or condition, because the problem states that the sum of these two numbers should be less than 50, but we got something greater than or equal to 50. That's a contradiction. I think most students put a contradiction there. I mean, that's fine. But maybe you should, especially if this is the first time you're doing the indirect proof, you can specify clearly, contrary to the condition or hypothesis that the sum of these two numbers is less than 50. So we are given that the sum should be less than 50. We found out the sum is greater than or equal to 50. That's a contradiction. So whenever you do the second step, you should always get a contradiction. And the last step, you can say the original statement is true. And sometimes we omit that. We just say, okay, the property is established, the claim is proved, the proposition is proved, if you want to just say that. So the main thing is to reach a contradiction. So follow the steps. Now let's go over the steps for mathematical induction. So that's the step for indirect proof. Mainly two steps. What about mathematical induction? What is the first step? We call basis step. And what do you do in your basis step?
Make sure the left side and right side are equal.
Huh? Wait, say it again?
Make sure both sides of the equation are equal. Or
yes, that's right. Basis means, at the end of the class, last Wednesday, I used the dominoes to the game of dominoes, similar to the proof of mathematical induction. So when you push down the first domino piece, this is like doing that. You always start with, you want to show both sides are equal, left equals right, for n equals 1. Well, the problem asks us to prove left side equals right side for n equals 1, 2, 3, 4, 5, 6, all the way to infinity. But we only going to do one case. If n equals 1, we prove they are equal. And then we do the induction step, inductive step. And what do we prove in the inductive step? If we show if the formula is true for what? N equal to k, we prove. Then part is what we need to prove. Prove what? Yes, that's right. To prove the formula is true for n equal to k plus 1. That is the main step. The difficult part is right here. Usually basic step is very easy. Simple algebra. Replace n with 1 on the left, on the right. On the left side, be a little careful. It's just going to be one number. But on the right side, it's very easy. Replace n with 1. But the difficulty part is inductive step. Okay, so we did that example last time. Today I'm going to do another two more examples. I'm going to prove 1 cubed plus 2 cubed plus 3 cubed. And your homework question is going to be doing squared. Plus dot 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 plus n cubed equals. There are two ways to write the right-hand side. I'm going to do this way because this way is easier. Some textbooks may have put it in a different way. This is the way they put. But if you use algebra formula, when you square fraction, you square the top and square the bottom. So 2 squared is equal to 4. The top, when you square the top, it's a product. So you can square the first factor, n squared, and the second factor, n plus 1 squared. So I went ahead and use the algebra formula to get the simplified one. Because otherwise the writing is going to be, you got to put a lot of parentheses. There's parentheses inside, the parentheses outside, and it's not very easy to do. Okay, so now let's start with the basic step. They will always specify what kind of integers this n takes. Most of the time it starts from 1 or 0. Sometimes they start from 2 or 3 or 5. It does happen sometimes. So pay attention to that smallest n. Step 1, basic step. All right, so what do I do in the basic step? So what would be the left-hand side? Yes.
1.
1 cubed, right, which is 1. You can simplify it to get 1. What about the right-hand side?
1.
Yes. So you replace that n with 1 and simplify that, you get 1 plus 2 squared, which is 4 over 4. That is still equal to 1. So now you can say the left-hand side equals right-hand side. Okay, so far we proved if n equals 1, we're going to get 1 cubed equals 1 squared times 1 plus 1 squared over 4. We simplified both sides, and we found out they are both equal to 1. So that tells us they are equal. So this formula is true if n equals 1. But you also have to show this formula is true for n equal to 2, n equal to 3, n equal to 4, n equal to 5, and 6, and 7. There are infinite many cases, which we cannot do, right? So that's why we are using induction. We're going to do an inductive step. Okay, I just went over this. In the inductive step, you always assume the formula is true for n equal to k, and try to prove the formula is also true for n equal to k plus 1. So what do we assume here? We're going to assume this formula is true for n equal to k, right? So can you write on the formula for n equal to k? Somebody wants to chime? Morgan?
It would be 1 cubed plus 2 cubed plus 3 cubed plus the 3 dots plus k cubed.
Yes, that's the left-hand side. What about the right-hand side?
It would be
K cubed on
The
top.
right, that's a square here. The right-hand side, right here, replacing n with k.
Then K squared.
Uh-huh.
Then in parentheses, K plus 1 squared.
Yes.
And then
And? Yes, right. Okay, so everybody clear how I got this? Okay, so we write down the formula for n equal to k. All you have to do is to replace that n with the letter k. All right, so we know this is true, but we want to prove the formula. This formula is true for n equal to k plus 1. I can put a k here too. Now, let me write down the formula for k plus 1 somewhere. Down here. So if you can put it on the scratch paper if you want, or if you want to put it on your notebook, you can leave. I would say at least maybe 4 lines here, so you have enough space to do the algebra work here. So now we want to prove. Go back to look at the inductive step again. So in the inductive step, we want to, if the formula is true for n equal to k. So this is the formula for n equal to k. We want to prove the formula is true for n equal to k plus 1. So if we want to prove the formula is true for n equal to k plus 1, we need to know what the formula looks like. So that's why usually you will have to write down that formula for n equal to k plus 1. Megan, do you want to try? What would be the formula if n equals k plus 1?
1 cubed plus 2 cubed plus 3 cubed plus ...
Uh-huh.
K cubed plus k plus 1 cubed.
Yes, good. On the right-hand side?
K plus 1 squared. K plus 1 squared.
Okay, let's go ahead and combine that k plus 1 plus 1.
K plus 2
Yeah. And?
over 4.
Yes. Okay, so everybody clear how we got this? Okay, so now the only question left to do is look at these two formulas. That's a formula, and that's a formula. That formula is for n equal to k, that formula is for n equal to k plus 1. So it's like asking to do, if this is true, please prove that one is true. Okay. So how do we use that to prove this one? Use the one on the top to prove the one on the bottom. Any suggestion? Yes, Curtis?
Insert the right side, or for m equals k, use the right side and plug that in for 1 cubed plus 2 cubed plus 3 cubed plus ... and then all of that plus k plus 1 cubed.
Okay, all right. You did a different way using substitution, right?
Yeah.
So you're saying, okay, well, look at the left-hand side. It has 1 cubed plus 2 cubed plus 3 cubed plus all k cubed. And that part, we already know. When we add in all these numbers, all these cubes, what do we get? That, right? So we can, when I see this, I can go ahead and replace it with k squared plus k plus 1 squared over 4. And add that part. And next step to prove that is equal to the right-hand side, right? Yes, that's one way to do the question. Last time I did a different way. What was the other way I did? You could do substitution. Yes, this will work if you like this way. The other way to do the problem is I'm just going to compare the left-hand sides of these two formulas. I realize in order to get the left-hand side, I can add k plus 1 cubed to both sides of the equation we have, right? That's the other way. So both works, whatever way you like. So this is the way I usually like to do. So I add k plus 1 to the left and add k plus 1 to the right. From algebra, we know that if you add the same thing to both sides of the equation, it's not going to change the equation. So now we have 1 cubed plus 2 cubed plus 3 cubed plus dot 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 plus k cubed plus k plus 1 cubed equals adding these two. So in this problem, there's a lot of algebra that we have to do here. K plus 1 cubed. All right, so either way, you're going to end up with this fraction, k squared plus times k plus 1 squared over 4 plus k plus 1 cubed. Or you can look at what Curtis did. He took the left-hand side and replaced that sum of the cubes of the first k numbers with that fraction and still end up with the same thing. So the next thing left is to show, well, which one do we want to prove? We want to prove this one right here. The right-hand side is k plus 1 squared times k plus 2 squared over 4. Not that expression. So we have to show they are equal. So that's the algebra work. Now, how do we show these two are equal? What algebra work can we do? So one way you can do is to add these two. How do we add them?
Common denominator?
Yes. Yes, common denominator. So put a 1 under there. What is the least common denominator? 4, right? So we're going to multiply the second fraction, both top and bottom, by 4. Okay. Now we can add the numerators. Keep the denominator 4. Add the numerators. Some of the steps can be omitted, like if you could just work it on here, just times by 4 times by 4, to save some writing. That's what we end up with. Go back to look at the formula that we want to prove, the right-hand side. That is what we need. We need a 4 on the bottom, which we already have. And we need a k plus 1 squared times k plus 2 squared on the top. Well, we are kind of close, but there's still plus here, so it's not exactly the same. Okay, so what can I do next? To show that the top I have is equal to the top that we need. Multiply everything out to show they're equal. That's one way, which is a little tedious because if you multiply everything out, you're going to get k squared, and then you have to you do FOIL here and distribute it. And k plus 1 cubed, it's even harder, right? It takes more time to do. And you multiply this out, it's also going to be time consuming. So usually we don't, it is correct solution. In the past, we also had a student who liked this way, but that's not the way I like to do because it takes quite a bit of time. Because our goal is not, it's not an algebra question to, if I ask you to perform the indicator operations, you have to multiply everything out. But right here, we don't need to do that. All we need to show is this fraction is equal to that fraction. So I can do factoring instead of multiplication. Factoring and multiplication, they are opposite, kind of reversing operations. So how do we do factoring of the top? What type? Greatest common factor, right? They have a greatest common factor, which is squared, right? So that has a k plus 1 squared here. That has 3 copies, which you can take 2 out. Now we factor out k plus 1 squared, and there's going to be a k squared. Factor out a k plus 1 squared, there is going to be a 4 times k plus 1. And we're getting close. Now look at the fraction we need. K plus 1 squared, we already got that. All we have left is to show this parenthesis matches k plus 2 squared. And if you look at it, k squared plus 4k plus 4, that's exactly k plus 2 squared. That's a trinomial. I'm going to go ahead and put k plus 2 squared right here. Okay. So now, that's the right-hand side. And the left-hand side we had was that. So we got exactly what we needed to prove. 1 cubed plus 2 cubed all the way to k plus 1 cubed equals this fraction. And that's exactly what we had at the very beginning. That's what we need to prove. Okay. All right, so we can stop right there. Any question?
Is there like a sentence, like you want us to put into that, like, wrap it up, or is it okay to do it, but,
Yeah, you can leave it there. If you want to say one more sentence, it would be like, so the formula hold is true for n equals k plus 1 if you want to do that. But if you stop there, that's perfectly fine. So the formula is true for n equal to k plus 1. Now, next, we're going to do one more example. Why don't you- Okay. So I'm going to 1 times 2, 1 times one times 2 plus 2 times 3 plus dot 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 times n minus 1 times n equals equals fraction of 3 n minus 1 times d times Okay, so mathematical induction. First, n is, in my case, n is greater than or equal to 2. The basis step. What do we do in our basis step? Yes, show this is formula is true for n equal to 2. So I'm going to write down n equals 2. On the left-hand side, what do you think we will get? Left-hand side. Is it better? Say it again. 1 times 2 plus 2 times 3. Do we need a 2 times 3? How do I know how many turns will I take? You can take this number and plug into the general formula. So if I replace n with 2, what do I get? 2 minus 1? 1 times 2. That would be the same as the first one, right? So which means you're not going to have another one. Okay, so the left-hand side would just be 1 times 2. Okay, does it make sense? Like how I found out I only need to take this one, I don't need another one. Okay, it seems like, well, n equals 2, you should have two terms, right? Sometimes, yes, it's like that, but in this case, it's not. All you have to do is replace n in a general formula. The last term is always a general formula. If you replace n with 1 or with 2, you're going to get 1 times 2, which is the same as the first one. If the first term in a sequence, if the first term is the same as the last term, which means there's only one term, okay? So now we have 1 times 2. If all numbers are different, Well, sometimes we may have the same thing, 2, 2, 2, 2. The first is the same as last, right? But over here, as you can see, every number is different. That's 1 times 2, which is 2. 2 times 3 is 6. So every number is different. And the last is the same as the first. That means there's only one possibility. The first is the same as the last. So you only have one term here, which is equal to 2. Now the right-hand side, using algebra, just replace that n with 2 there. So we got 2 minus 1 times 2 times 2 plus 1 divided by 3. So we got 1 times 2 times 3 divided by 3. That gives us 2. So as you can see, both sides are equal to 2. So left-hand side equal to right-hand side. So far, we have proved that this formula is true for n equal to 2 because they are equal. Now let's do the inductive step. What do we assume here? Inductive step. Elsa? What would you, okay. In the inductive step, we're going to assume this is true for n equal to k. So what would be this formula if n equals k?
1 times 2 plus 2 times 3 plus dot 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 plus k minus 1 times k.
Equals. What about the right hand? Okay.
Times
Go ahead.
k plus 1 over 3.
Okay. K minus 1 times k plus 1 over 3. So replacing n with k. Okay, so that's what our assumption is. But what do we need to prove? And where does this come from? Replacing n with k. So that's like, n, if you replace n with k in the formula, you get that. So next thing you want to do is to write down the formula for n equal to k plus 1. Austin, do you want to try? What would be the formula if n equals k plus 1?
1 times 2 plus 2
Okay. 1 times 2 plus 2 times 3 plus dot 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 plus,
that's k times
yes, that would be the last term, but usually we would like you to also write down the last 2 terms in this case. Yes, the one right before that. Now, what about the right-hand side? What will be on the top if n equals k plus 1?
k plus 1.
Yes. All right. All right, so we got both formulas. Does anybody have a question about the second one? The first one is easy to see because all you have to do is to replace that n with k. K minus 1, k, and k here, k there. But when n equals k plus 1, we do have to do a little bit of work. When n is k plus 1 minus 1, we go ahead and simplify that to get a k. And replace n with k plus 1 here. K plus 1 plus 1 will be k plus 2. On the left-hand side, because we're replacing n with k plus 1, so that becomes k plus 1 minus 1. That gives us k. That becomes k plus 1. So that's why we got the last term, k times k plus 1. But in order to compare to the formula for n equal to k, we want you to write down the last 2 terms instead of just the last one. So the second to the last term will be the same as that, where n equals k, so k minus 1 times k. Okay, so following the pattern to write the left-hand side. Now, you could do what Curtis said before, to do substitution. So if you do substitution, you will see, okay, I noticed that this whole thing is exactly the same as what we have there in that formula, right? So that whole thing, I can replace it with a simple fraction. So when I see that, I can replace with that fraction there, right? Okay. And then you're going to add this fraction and k times k plus 1 to show that is equal to the right-hand side fraction. Or you can do what I did to compare the left-hand sides. I noticed that we're missing k times k plus 1. That's why I can do times k plus 1, add k times k plus 1 to both sides. And after we add that, the left-hand side would match the left-hand side we need. So 1 times 2 plus 2 times 3 times plus dot 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 plus k minus 1 times k plus k times k plus 1. So that would be the one we need. On the right-hand side, it will be the same as substitution. We're going to add k minus 1 times k plus 1 plus k times k plus 1. Okay, in order to do that part, it's the same as what we did before. Equal denominator and numerators. So I'm going to go ahead and put a 3 down here and a 3 up here. Multiply both top and bottom by 3. Now we can get something like this. I'm putting them together so it's better. That's the first top plus the second top, 3k times k plus 1. So now that what's left to do is to show these two fractions, this one and the one we have, to show they're equal. And how do we do that? The bottom match, 3, 3, right? The bottoms, 3 and 3. So the top, all you have to do to show this top is the same as that top. What can we do? Factor out a k times k plus 1. There's a k here, there's a k there. There's a k plus 1 here, there's a k plus 1 there. If you factor out a k times k plus 1, what's left? Okay, factor out this k, both k's, both k plus 1s. We have k minus 1 plus 3, which is k, what? K plus 2, right? Okay, so when we do factoring, you will get that. I'm out of space, so I'm not going to write down another one, so pretty much you go from there to that, okay, just by doing factoring. Any question? Okay, so far we are, so far we're going to, we use the mathematical induction to prove the first type. If you look at the problems we just proved, the left-hand side always has something like dot, 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 and dot, 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 like what we call series in calculus, and also the one with the cube. But we can use mathematical induction to prove other type of questions. So this is the first type. The second type we're going to do is to prove divisibility. So we're moving on to section 4.3, mathematical induction continued, part 2. Part 2. Before we look at the type of question, I want you to go over some of the algebra formulas, because we're going to use those. Okay, first formula is x to the n power times x to the n. What do we get? Does everybody know this formula? Yes? Okay. So we use that. We learned this in algebra class. We also use this in calculus class. And so, if I give you 2 to the k power times 2, what's the answer? 2 to the k plus 1. Because 2 means 2 to the first, right? Okay. So you kind of have to be familiar with this. Sometimes we have to, you need to, if I give you something like 2 to the k plus 1 and 2 to the k, I want to ask you 2 to the k times what equals 2 to the k plus 1. You also need to know it's times 2. Okay? So that's one of the formulas. The other one is combining like terms. I think everybody knows what x plus x is, right? Equals what? 2x, right? But if I give you 2 to the kth power plus 2 to the kth power, does anybody know what we get? Simplify this. What is 2 to the kth plus 2 to the kth? Does anybody know? 2 to the 2k? 2 to the 2k, that would be for multiplication. So if you do multiplication, that would be keeping the base, adding the exponent k plus k, right? The previous formula that we went. Notice that the first formula I went over is for multiplication, but the second one is addition. Okay, 2 to the k times 2 to the k, by using the previous formula, you keep the base x, in this case 2. You add the exponents, k plus k, which gives you 2 to the 2k. But what if it's addition? Addition is not going to give you 2 to the 2k. Huh? 4k? No. You cannot get 4k either. Okay. 2 to the, if you think of 2 to the k as the variable x, what do you get? 2x, right? What did you do? It just means pretty much why does x plus x equals 2x? Because there are 2 copies of x, right? So when you add 1 copy plus another copy, you got 2 copies of x. So in this case, we got 2 copies of what? 2 to the k, right? So all you have to write down is 2 copies of 2 to the k. 2 times x. This means times, right? So we are replacing x with the 2 to the k. 2 times 2 to the k. Does that make sense? Okay. So what is 2 to the k plus 2 to the k? It's 2 times 2 to the k. And you can continue to use the formula for multiplication to get a 2 to the k plus 1 or 1 plus k. Right? Yes? Okay. So similarly, if I ask you what's 3 to the k plus 3 to the k equals 6 to the k?
6 times 3k.
Huh?
1 plus k.
3
6 to the 1 plus k.
No. Don't skip the step, okay? What did we just say? When you do addition, you're going to get how many copies 2 to the k?
2 times 3 to
2
the
times
k.
3 to the k. Which, can we multiply then any further? Can we multiply them any further? No, because this one has base 2. 2 to the first times 3 to the k, you cannot combine multiply them. But if I give you 3 copies, 3 to the k plus 3 to the k plus 3 to the k, what do you get now? How many copies? 3 copies of 3 to the k, right? Is that right? Okay. And you can continue because they have the same base. That would give you 3 to the k plus 1 or 1 plus k. Okay. All right. Well, I think if I give you k squared plus k squared, everybody knows what's the answer is, right? What's k squared plus k squared? 2k squared, right? Because you got 2 copies of that, right? Even if I switch it and you get 2 to the k plus 2 to the k, you still get 2 copies of 2 to the k, right? Whatever that is. If you have k plus k, you get 2k. If you get k squared plus 2k k squared, you get 2k squared. If you get 2 to the k plus 2 to the k, you get 2 copies of 2 to the k, which can be simplified to k plus 1. Okay. So these are some formulas from algebra which will be used in the proof of this section. So now we start with example. We want to prove for all integers and greater than or equal to 1, 2 to the 2n minus 1 is divisible by 3. That is an example from the textbook in this section. we did this type of question before, divisibility. How do we show a number is divisible by 3? To show this number is a multiple of 3, but how? And how do you show this is a multiple of 3? Yes, this number, you would have to show this number is equal to something times 3, right? Or 3 times something. In other words, you need to be able to factor out of 3. But look at this. Can we factor out of 3? Can we? No, we can't, right? We talked about in previous section when we talked about division by cases, we learned a different way. If you cannot factor out of 3, but maybe you could, for example, if I want you to show this number is divisible by 3, which you can't, but if you do 3 cases, maybe you can, right? N equals 3k or 3k plus 1, 3k plus 2, you will be able to factor out of 3. But in this case, even if I do 3 cases, will I be able to factor out of 3? No, because it doesn't matter how you change this n here. There's a minus 1 there. There's no way you can factor out of 3 from here. You see that? Okay. So there's no n here that you can. So the way we learned before to do by cases will not work either. So we are going to use mathematical induction to prove this. Step 1, basis step. Okay, so what do we do in the basis step this time? Yeah, substitute 1 for n. So in this case, what do we get if n equals 1? It's not going to be a formula we had before, something equals the left-hand side equals right-hand side. What we get is this statement. So you're just replacing n with 1. You're going to get 2 squared minus 1 is divisible by 3, right? So you need to show 2 squared, replacing n with 1. Minus 1 is divisible by 3. Is this, can we prove this? 2 squared minus 1, which is what? 3, right? 3 is divisible by 3. Very easy. So as before, the same as before, the basis case is usually very easy. Most of the time it's very obvious. 3 is divisible by 3. You don't have to prove anything at this point. Now, inductive step. You write down the statement for n equal to k. Well, so what will be the statement if n equals k? 2 to the 2k minus 1. So we assume 2 to the 2k minus 1 is divisible by 3. Now, replacing n with k. As before, what do we need to prove? We need to prove this statement is also true for n equal to k plus 1. So if n equals k plus 1, what will this statement become? Replacing that n with k plus 1, right? Be careful when you substitute k plus 1 for n, remember to put parentheses there. Okay, so you're going to prove, we want to prove 2 to the 2k plus 1. If you don't put a parenthesis there, what's going to happen? You're just going to get 2k plus 1, right? But in fact, what we want to do, you have to distribute 2 to both of them, so you're going to get 2k plus 2 there. So we want to prove 2 to the 2 times k plus 1 minus 1 is divisible by 3. But this time we don't have left-hand side, right-hand side yet, but if we use the definition of divisibility, so let's take a look at these two statements. It's like asking to prove if 2 to the 2k minus 1 is divisible by 3, prove 2 to the 2 times k plus 1 minus 1 is divisible by 3. Okay, now think about the definition of divisibility. If I know a number is divisible by 3, that tells me I can write this number as what? By the definition of divisibility, I know this number, whatever that is divisible by 3.
3 times some integer.
Yes, very good. So that's a definition you have to memorize. Like I said, in 3070, you are still going to use that definition again to do a lot of proof problems. Well, I already have k there, so let's try to pick a different integer. And we already used the letter n, so maybe to try to avoid n and k, so I'm going to use m, where m is an integer. Okay, if a number is divisible by 3, you must be able to write this number as 3 times the integer. That's just from the definition. Okay, but what do we want to prove? We want to prove this number, which is different from that number, is divisible by 3. So similarly, well, if you want to prove, if you know this is divisible by 3, you know this integer exists. That's why we can pick letter m for that. But if you want, they ask you to prove this number is divisible by 3, we don't know whether this number exists or not, right? So for example, if I give you a huge number, say 1, 1, 1, 7, 8, 9, I want you to prove this number is, this number is divisible by 3. But before you prove it, you won't know whether this number is divisible by 3 or not, right? So you have to show me. How do you show that? How do you prove this number is divisible by 3? You need to show, okay, I can write this number as 3 times the integer. You just have to tell me what the integer is, right? So similarly, right now, here, we want to prove this number is divisible by 3, which means you have to show me this number can be written as 3 times some kind of integer. You got to show me what that integer is. It doesn't have to be a specific number. It could be a variables we had before. So how would I find this integer? You can either use substitution like Curtis did before. Maybe, I think for this case, maybe substitution is easier. So we start from the left-hand side. We want this number that's given. And try to work this out. So the one we want, the number we have is 2 to the 2 times k plus 1 minus 1. So start with this. I want to factor out 3 from here. Right now I can't, but I can do some algebra work. So first of all, distribute that 2 to get 2 to the 2k plus 2 minus 1. Well, I got this equation right here. I haven't used it. So later you will see how to use this. So far, let's work on simplify the number a little bit. Now, use the definition. How do I do substitution now? How do we do substitution now? Because that's 2 to the 2k plus 2, but that's 2 to the 2k. I cannot just substitute. So you have to do something to change that. In order to substitute the 2 to the 2k, you have to get 2 to the 2k, right? So what do? This part, that's the question that I asked you at the beginning. If you know this and ask you, that is equal to the k times what? Can you tell? Yes, 2 to the second, right? Can everybody see why? We're using the formula backwards. So this is what we're going to do. We're going to break this down as 2 to the 2k times 2 squared. And still there's a minus 1. Okay, that part can be substituted. Well, what do we substitute with? That part can be replaced by what?
M. Oh wait.
What?
3m.
3m? Well, 3m, there's a minus 1 there. So we are just replacing this part. There's no minus 1. So we should do something to get rid of that minus 1. What can we do? You can move to the other side, or you can just say add 1 to both sides, right? If you add 1 to both sides, you are going to get 2 to the 2k equals 3m plus 1. You guys see that? Okay, now I can substitute 3m plus 1 for 3m plus 1 for 2 to the 2k. You see that? Okay, so now go back here. When I see this, I replace it with 3m plus 1 times 2 squared, which is just 4 minus 1. Make sense? Okay, now let's continue. Can we factor out a 3 from here? By looking at this, not yet, right? But if you distribute, I get 12m plus 4 minus 1, and combine like terms. Can we factor 3 out of there? Yes. Plus 1. So, don't forget, where did we get, so we start with this, and we end, originally, you cannot factor out of 3. So we simplify the number using the formulas, and did a substitution right here, and we are able to factor out of 3. So now what can we say? If you just look at the beginning and the end, what does this mean? If you can write something as 3 times an integer, what do we say? 3 divides that number. Well, that number is by 3, right? And why is this an integer for m plus 1? Because m is an integer, right? If m is an integer, for m is plus 1 is an integer. So you can say, therefore, 2 to the 2k plus 1 is divisible by 3. Okay. All right, that's all for today.
Your meeting has ended.